For Module 19b, we're going to start really talking about entropy. You need to know and be able to use the following relationships. S is equal to K times Ln times W, and delta S of surroundings is equal to negative delta H the system over T. Understand and be able to correctly apply the concepts of spontaneous and non-spontaneous processes and entropy. Be able to apply the 3 laws of thermodynamics and be able to predict the sign of delta S for chemical or physical change. What do I mean by spontaneity? A key question, when is a process spontaneous? Another way to say this is thermodynamically favored. Reactions can be controlled by thermodynamics or by kinetics or by both or by neither. I want to know, when is the thermodynamics controlling the reaction? When is a process spontaneous? In thermodynamics, spontaneous means that a process is able to proceed on its own without being driven by an outside source of energy. Examples of this are like combustion of hydrogen. So remember, combustion is when you burn something in the presence of oxygen. If I'm combusting hydrogen, I would have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to form 2 moles of water. This is a spontaneous process. Meaning, once the reaction begins burning, it continues on its own. It continues without any sort of outside interference. A non-spontaneous process, so this would be spontaneous, would be the electrolysis of water. Which is the opposite process. I can take 2 moles of water and I can react them to form 2 moles of hydrogen gas and 1 mole of oxygen gas, but this is non-spontaneous. To get that reaction to happen, I can have a beaker with water in it, but I would have to connect this to a battery or some kind of power source. And at one end, I'm going to make hydrogen gas. The other end, I'm going to make oxygen gas. Non-spontaneous. I take the battery away, the reaction stops. So a process is said to be spontaneous if it occurs without outside intervention, but it may require activation energy. It may require a spark or an initiation to start, but once started, it's going to keep going on its own. Spontaneous processes are not necessarily rapid processes, though. It could be a very slow process. So again, example, combustion of hydrogen, electrolysis of water, melting of ice. This is spontaneous depending on temperature. Sodium chloride dissolving. Rust. All of these are going to occur, some faster than others. A chemical reaction that's proceeding towards an equilibrium is an example of a spontaneous change. Gibbs free energy, delta G, also just called free energy, is a measure of the spontaneity of a process. It's related to its temperature dependence. So Gibbs free energy will tell us if his reaction will be spontaneous or not spontaneous. Couple considerations. Number 1, processes that are exothermic tend to be spontaneous, but not all spontaneous processes are exothermic. How do I identify if a reaction is exothermic with delta H? Well, delta H will be less than 0. Or delta H is a negative value. Example here would be combustion. If I combust methane gas, delta H is less than 0. This is actually a very exothermic process. It releases a lot of energy. But again, there are many exceptions to this, and we have to be aware of that. Number 2, processes in which the entropy of the system increases tends to be spontaneous. That doesn't mean they are, they just tend to be spontaneous. Again, there are many exceptions here. So delta S is the change in entropy. If delta S is greater than 0, the process tends to be spontaneous. And I will do the example on the very next slide. But what if these two considerations are opposed to each other? Meaning that the exothermic process and the entropy, so the enthalpy, what if enthalpy and entropy are working against each other? Example of that would be melting of ice. How do I know, is ice going to melt? Melting of ice is H2O solid going to H2O liquid. And most people, if I say, is this process going to happen? People are going to say, yeah, of course ice is going to melt. The better question, though, is what temperature are we talking? It will melt if it's at the correct temperature. But, and we're going to talk about more specifics on this in just a sec, but melting of ice, the delta H here is positive. This is an endothermic process. Energy had to go into the system to make it melt. Delta S is also positive. Entropy is increased. Delta H being positive is not favorable for spontaneity. Delta S being positive is favorable for spontaneity. Entropy is, and the reason entropy is positive here is entropy is increasing the number of microstates I have, or the disorder I have. Something locked into a solid phase is a lot more ordered in structure than something in a liquid phase. A liquid phase has more disorder, so the entropy is favored. So in this example, whether or not the process is spontaneous depends on temperature. At 25 degrees C, the process is spontaneous. At -5 degrees C, the process is non-spontaneous. To determine if a process is spontaneous or not, we have a 5-star equation we're going to use. Delta G is equal to delta H minus T delta S. Let's delve a little more into entropy, though, just so we can really understand what's going on here. So, a more simplistic approach. Entropy can be thought of as a measure of the randomness or disorder of the system. More precisely, entropy is a thermodynamic function that is related to the number of microstates or arrangements available to the system. What does that mean? That can get kind of confusing to think about. What do I mean by microstates or arrangements? And, okay, the example is down here. I will talk about that in just a sec, but I'm going to put a different example right here. This goes with your notes just above, but I don't have space in that slide. So let's say that I have 2 flasks that are connected. And there's a stopper between the 2 flasks. One of my flasks is completely filled up and the other one is completely empty. So I have 1 liter. Let's just say we've got helium gas in here at 1 atmosphere. On this side, it's a 1 liter flask, but it's completely empty or evacuated. What happens if I open that valve? Well, most of us naturally assume that the gas, the helium on the one side, is going to fill both sides of the flasks. And that's correct. the gas is going to spread out to the total system. Now, I will theoretically have 0.5 atmospheres of helium gas on each side. The delta S here has increased. It is greater than 0. Now, instead of having all of helium contained on just one flask only, I've got it spread across twice the amount of space. It's increased the amount of disorder I have. It's increased the number of microstates I have. So I have the two identical flasks connected by a glass tube. There's a valve in the glass tubing. The flask on the left here contained all of my helium. The flask on the right was completely empty. The valve opened. The gas spontaneously expands. Spontaneously fills the flask on the right, and the entropy increases. What if I talk about the Boltzmann definition? So Boltzmann definition of entropy. S is equal to K ln of W, where S is your entropy, K is your Boltzmann's constant. Boltzmann's constant is equal to your gas constant R divided by Avogadro's number. So you can either remember R over NA because you already have those numbers, or you can remember Boltzmann's constant. I don't care which one you do. But that's how you find it. Ln is your natural log. And W is the number of microstates available to the system. So a system with fewer microstates has a smaller number of W and a lower S or a lower entropy. A system with more microstates has a larger W or a higher entropy. Higher option for the particles to exist. What do I mean by microstates though? How do I determine my microstates? Let's look at this example. The following model system has two glass flasks connected by a valve. If there's only four gas molecules, A, B, C, and D, how many microstates are possible? Well, I've got a left side and I've got a right side. How many possible states are there for these molecules to exist in? Let's add them up. For the left flask and the right flask, I could have A, B, C, and D all on the right, or all on the left, none of them on the right. I could have 3 on the left and 1 on the right. I could have A, B, C on the left and D on the right. A, B, D on the left and C on the right. A, C, D on the left and B on the right. Or B, C, D on the left and A on the right. I could have the opposite of that, where I only have 1 on the left and 3 on the right. A, B, C, D. B, A, C, D. C, A, B, D. Or D, A, B, C. I could have none on the left and all of them on the right. Or I could have 2 and 2. I could have A, B, C, D, A, C, B, D, A, D, B, C. But I can also flip it because there's 2 different flasks, right? So I could say B, C, A, D. I could say, hold on, that should say A, C, D, B. I could have B, D, A, C. I could have C, D, A, B. All of these are possible microstates. So this has 1 possible state. This has 4. This has 4. This has 1. This has 6. Overall, there is 16 overall microstates. That's just with 4 molecules and 2 flasks. They can get pretty complex. The increase in the number of microstates is what's increasing my entropy. It's increasing the number of possible places that these particles can exist. It's increasing the disorder of my system. How do I predict what it's doing? Predicting the sign of delta S. For a given substance, if the temperature increases, your delta S has increased. When you increase the temperature, you're giving the particles more energy to be able to move around. Generally speaking, gases have a higher entropy than liquids. Liquids have a higher entropy than solids. And solutions usually have a higher entropy than the pure solute and solvent, but there are important exceptions here. So, S of your gas, so entropy of your gas is a lot larger than entropy of your liquid, and entropy of the liquid is definitely bigger than the entropy of the solid, just not as large of an effect as on a gas. And why? Because solids have little movement to them. And solutions, if I have NaCl solid, I put this into water. I now have sodium ions floating around and chloride ions floating around. Instead of just one salt molecule, I've got ions galore. Delta S has increased. Can I predict this though? What can I say is a sign of delta S for each of the following processes? What I want you to think about is, as I'm going from a solid phase to a liquid phase to a gas phase, my enthalpy is increasing. My entropy is also increasing. One thing to note here is that enthalpy is going to be on a kilojoule scale. Entropy is going to be on the joule scale. They are not the same scale. Your effective entropy is much smaller than the effective enthalpy. When we give you numbers for enthalpy and entropy, we give you enthalpy in kilojoules and entropy in joules. You must make sure you're talking about the same units or you're going to mess up all your calculations. But let's, in general, phase changes for pure substances. If I'm going from a liquid phase to a solid phase, liquid to solid, I'm going to go, that's like looking at this transition right here. That is going from a less ordered state to a more ordered state. Delta S will be less than 0. Delta S is happiest when it can become more disordered. It's positive when it becomes disordered. Because I made it more ordered, my delta S will be less. What about going liquid to gas? Liquid to gas is this transition here. Delta S will be greater than 0. I'm going to more microstates. I'm going to a more disordered system. What about magnesium solid going to magnesium oxide solid and CO2 gas? Now in this one, you need to think about the types of things that are occurring, like what's reacting, what phases they're in, and also how many moles do you have. Here I have 1 mole, that's a solid, and I'm producing 1 mole of solid plus 1 mole of gas. Delta S is going to be favorable because I've created 2 moles from 1, or produced 2 moles from 1 mole. What about 4 moles of Fe solid plus 3 moles of O2 gas, giving me 2 moles of Fe2O3? Over here in total, I've got 7 moles, and I'm going to 3 moles. Delta S here, not favorable. Then why does it happen? Why does rust happen? Because it's thermodynamically favorable because of enthalpy. So it doesn't have to be both of them. It does not have to be both delta S and delta H being favorable for it to happen. One or the other could be controlling the system. But because I'm going from 4 moles, specifically, or from 7 moles, 4 moles of 4 moles of solid and 3 moles of gas to just 3 moles of solid, that is not favorable by entropy. N2 gas plus 3H2 gas. I've got 4 moles of gas. There should definitely be a 2 in front of here. Please fix that on your slide. I apologize. To 2 moles of gas. Not favorable. I'm going to less states. Delta S will be less than 0. And I've got ammonium phosphate, 1 mole, going to 3 moles of an aqueous solution of ammonia and 1 mole of, that should be a 4 right there, that should be phosphate, not phosphite, 1 mole of phosphite, so 4 moles total, and solid to aqueous on top of it, delta S will be greater than 0. So the second law of thermodynamics. The second law tells us that in any spontaneous process, the total energy of the universe always increases. The total energy of the system and surroundings, therefore, always increases. Delta S total is equal to delta S of your system plus delta S of your surroundings. Or you could write it as delta S of the universe is equal to delta S of the system plus delta S of the surroundings. As long as the delta S of the universe is positive, a process can be spontaneous. Even if delta S of your system is negative. Let me write that down. So as long as delta S of the universe is positive, a process can be spontaneous. Even if delta S of your system is negative. Therefore, delta S of your system can be negative for a spontaneous process as long as delta S of your surroundings is greater than the absolute value of delta S of your system. So, is it possible to have delta S of the system less than 0 for a spontaneous process? Yes, if delta S of the surroundings is greater than the absolute value of delta S of your system. What do I mean by that? I mean things like water, the liquid phase going to water in the solid phase. Delta S of the system here is not favorable. Going to a solid phase makes it more ordered. That is not favorable. But this is spontaneous when the temperature is less than 0 degrees C. My surroundings have a larger positive delta S my surroundings. So an exothermic process increases the entropy of the surroundings. An endothermic process decreases the entropy of the surroundings. And I can find, there should be a division line here, I can find delta S of the surroundings by taking the negative delta H of the system divided by my temperature. And the third law of thermodynamics tells me that the absolute entropy of a pure, perfectly ordered crystalline substance at 0 degrees K is 0. Why is this important? Because all entropy values can be measured relative to absolute 0 of entropy at 0 K. So we're assuming that this is at 0 K, so this is temp. This is your entropy in joules per Kelvin. 0 Kelvin, 0 entropy. This is looking at water specifically. If I had 1 mole of water at 1 atmosphere, it would be a solid phase until it hits 273.15 K. And then it would be a liquid phase until it hits 373.15 K. And then it would be a gas phase. So, melting and evaporation. Why is this important? Because, again, all entropy values can be measured relative to absolute zero of entropy at 0 K. What that means is that the absolute entropy of a substance can be known at any given temp. If 1 mole of a pure, perfectly ordered H2O solid, which has an absolute entropy of 0 joules per Kelvin at absolute zero, is gradually increased to 298 K at room temperature, the entropy would rise to 69.9 joules per K. Room temperature being 298 K or 25 degrees C, my entropy would equal 69.9 joules per mole K. Joules per K, because it is for 1 mole. So the entropy increases when a substance changes from solid to liquid phase or from liquid to gas phase. The entropy increases with the number of moles of a gas in a chemical reaction as well, and entropy increases during the dissolution process. Why do I care? What's the significance of all of this? We can know the absolute entropy of a given substance at a given temp. However, we cannot know the energy, the enthalpy, the Gibbs free energy. We can only know change in energy, change in enthalpy, change in Gibbs free energy.